Okay, so we are talking about vector space. In the last class, we have discussed the linear sum of the two subspaces. So, today we will talk about linear combination of some vectors. So, let us just recap. So, let V be a vector space over a field F. So, basically what we have a non-empty set V and we have another non-empty set F, and on V we have a vector addition, and on field we have a scalar, field element are called scalar. On field we have a scalar addition and scalar multiplication, and then we have a external operation which takes one vector scalar from here. This is the scalar multiplication and takes a vector from here and it gives a vector in here. So, this is a x vector, this is a. So, this will be a. So, this is an external composition and these are all binary operator, and we know this will be called vector space if this form a abelian group and we have certain property with the this scalar multiplication together with this vector addition. So, this we have already discussed. Okay. Now, suppose we take two vector from this vector space x and y, let x y belongs to V be two element, which element of V is usually called vectors and element of F are usually called scalar, but they are just a set. Okay. Then this collection, if you take say A B, A x means this is the A x plus B y. So, this is basically nothing but A is a scalar, we XOR with this x bar, sorry y bar. This is a linear combination of where A B are coming from field, and if we run this for all A B, then this will give us a set, this will give us a set. So, this is a vector. Okay. And for simplicity we just write this A x plus B y kind of, this plus is the vector plus. So, we have to be little careful with the symbol, but for simplicity we can use this. Okay. So, this is basically called linear combination of two vector x and y. This expression is called linear combination of x and y. Okay. So, if we take all such linear combination, then it will give us a, I mean this is a this collection is a set, and this is called linear span of these two vector. Okay. So, instead of two vector we can have many vectors, we can have say 3 vectors or we can have say n vectors, okay, or we can have k vectors say x 1, x 2 or say alpha 1, alpha 2, these are the vector alpha 1, alpha 2, alpha 3, alpha k. Suppose we have k vectors, okay, and these are coming from V, this is a subset of V. So, all the alpha are vector. Now, we can define a linear combination of this vector. So, if we take this C 1 alpha 1 plus C 2 alpha 2 plus this plus is the basically vector addition. So, we have to be little careful C k alpha k. So, this is also a subset of V, this is also a member in V, and this is true for all C i's. This is true for all C I. So, again we have to be little careful here, this is actually the scalar multiplication and this is actually vector addition, but for simplicity we are taking this as this expression. Now, this is again a vector, this is called linear combination of, this expression is called linear combination of of these vectors alpha 1, alpha 2, alpha k. Okay. Now, if we vary these Ci's, Ci are the scalar coming from the field element. If we vary these Ci's, this will give us different vectors. Now, if you take this collection we denote by say some set. If this is S set, this collection is denoted by L of S basically. L of S is the basically this set where where this Ci's are coming from. This is if we vary this scalar. So, this will give us all possible linear combination by these vectors, and this is called linear span or span on this set, linear span of the set S, and this is denoted by this. Okay. Obviously, this is a subset of V, L of S is a subset of V, non-empty subset, because if we take each of these alphas belongs to this, because if we take this C 1 is 1 and C i's are all 0. So, each of these alphas are belongs to. So, obviously, this is non-empty. Now, the question is whether this will again form a vector space or not. So, the question is whether L of S is a subspace or not. Yes, L of S is a subspace. So, that we have to prove. We have to show this linear span of S for any S is a subspace. So, let us just try to prove that. So, set of all linear combination of some vectors is again form a vector space. So, this is a theorem, linear span of a non-empty set, non-empty set of vectors is a subspace of the vector space. How to prove that? So, let us try to prove that. So, let V be the vector space, okay, and S is that non-empty subset. So, at least there are one element in S. Suppose S is basically say alpha 1, alpha 2, alpha k. Suppose there are k element in S. These are all basically vectors. Now, L of S is the linear combination of this. So, L of S is basically the all possible linear combination of summation of C I alpha I, where I is basically 1 to k and C I are coming from F scalar for all I. So, this is the way we now to show this is to be vector space, we have a necessary and sufficient condition. So, for that what we need to show? We need to take two vector from here, two element from here x and y belongs to L S, and we have to show A x bar plus means this is again this is a vector plus B y bar is also belongs to this, and if this is true for all A B and all x y, then we are done. Then this is a sufficient condition to become a non-empty set to be a again form a vector space. So, we are going to show this, we are going to prove this. So, this is how to prove this. So, we have to take two x y from this L S. Okay. So, x y belongs to this means x will be represent some C I alpha I is equal to 1 to k, and again y will be represented as some d I alpha I, where these are coming from the scalar. So, this C I d I are coming from this field. So, I is equal to 1 to k. Okay, now, we take two arbitrary vector A B. Now, for all A B belongs to F, what is this A x bar plus B y bar. So, this is again scalar multiplication, and this is again scalar multiplication, this is again vector addition, but for simplicity we are just writing in this way. So, this is nothing but, so if we just a x bar summation of C I, the sum is again vector sum. Okay. For simplicity we are writing in this way, otherwise we can write in this in a vector addition way. Sum C I, small c I, C I is a scalar, alpha I is equal to 1 to k plus b of again summation of d I alpha I is equal to 1 to k. Now, if we use the properties of the scalar multiplication along with the property of the vector addition associated property, so we can just write this as sum of a c I plus b d I into alpha I, this I belong 1 to k. Now, this is nothing but, this is again a scalar quantity, because this is scalar multiplication, this is scalar multiplication, this is scalar addition. So, this is again some summation of some d we have used some E I alpha I is equal to 1 to k, where E I is nothing but this expression a c I plus b d I. So, this is also a scalar quantity. So, that means this belongs to L of S. So, then by that theorem, that is necessary and sufficient theorem, L of S is a vector space. So, the linear span of a set, so L of S is a vector space, it is a subspace of V. Okay. This is the minimum subspace of V which contain S. Why minimum subspace? Because there is no other subspace which is less than this which can contain S, because then if we can prove this by contradiction. If suppose there is a set, there is a subspace which contain S is minimum than this, then we can reach to a contradiction. So, this is the minimum subspace containing S, or minimum subspace means minimum number of element in the minimum set containing S. Okay. So, this is called linear span of a set. Now, we can have some result on this linear span of a set. This is very easy to verify. First result is linear span on linear span is basically, this is quite obvious, because if you take the linear span, it is collection of, if S is say alpha 1, alpha 2, alpha k, then linear span itself is basically linear, all possible linear combination of this set. Again, if we take that set and if we take the linear span, so eventually it will give us a linear span of these alphas, that is equal to this. Again, we can formally prove that by taking this as a subset of this as a subset of this, but that will be not very difficult to show. Okay, the second theorem is, if we have two subset, subset S and T, then linear span of S T is basically linear span of S plus linear span of T. This is also can check very easily, because if we take this S set C alpha 1, alpha 2, alpha m, and T set is basically beta 1, beta 2, beta n, then their union is basically all alphas, all betas. Maybe there are some common element, we do not know, all alpha, all betas. Now, if you take the linear combination of this union, then this will give us linear combination of alphas and linear combination of betas. So, we can separate these two out, we can take the linear combination of alpha here, we can take the linear combination of betas here in T. So, again we can easily show this is a subset of this is a subset of this. So, then these two sets are same. Okay. So, these are proofs are quite trivial. Now, we will define what do we mean by linear dependent, linear independent of a set of vector. Linear dependent and linear independent. So, suppose we have a set of vectors say alpha 1, alpha 2, alpha k. Okay. Now, we call this set S say is linearly, this is the definition, linearly dependent. So, these alphas are linearly dependent if this suppose we have a linear combination which giving us 0 alpha 2 c k alpha k 0 vector actually. If this is 0 vector for some c i's, for some non-zero c I. So, if there exists some non-zero c i's for which this linear combination is 0, then we say this set is linearly dependent. Okay. This is the definition. Definition of linearly dependent. Now, if there exists some non-zero element, non-zero scalar for which this happened, then we call this is a linearly dependent set. Now, when we call linearly independent, if this is 0 means all c i's are 0, that means we cannot able to find any non-zero c i's such that this expression will give us 0 vector. Then we say this set will be the linearly independent set. So, similarly, so we say this is the definition of linearly independent, linearly independent, linearly independent set of vectors. So, we say this set alpha 1, alpha 2, alpha k are linearly independent set of vector if c I alpha 1 plus c 2 alpha 2 plus dot 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 c k alpha k is 0 vector, then all the c i's must be 0. So, all the c i's must be 0. So, there should not exist any non-zero c I for which this linear combination will give us a 0 vector. So, that means, if any linear combination is a 0 vector, then the coefficient must be 0, the scalar must be 0. So, that means, all c i's are basically 0 vector, a 0 scalar. Okay, the c I are coming from F, the field. Then we say this is a this set is a linearly independent set of vector. If no such non-zero c I exist. So, that means, if the linear combination is a 0 vector, then all the c i's must be 0. So, this is the definition of linearly independent set of vector. Okay. So, now we will quickly take some example of some linearly dependent and independent set of vectors. So, let us take some example. Okay. Now, suppose we have a set of vectors say 2 1 1 from R 3, our V is R 3. Okay. 1 2 2, then 1 1 1. So, this is our alpha 1, this is our alpha 2, this is our alpha 3. So, you want to check whether this set is a linearly dependent or linearly independent set of vector or not. Okay, so for that we choose C1, C2, C3 such that C1 alpha 1 plus C2 alpha 2, this plus is again the vector addition, C3 alpha 3 is equal to 0, 0 vector 0 0 0. So, this will give us basically 2 C1 plus C2 plus C3 comma C1 plus 2 C2 plus C3 comma then again C1 plus 2 C2 plus C3 0 0 0. Then this implies we have 3 equations in which 2 equations are same, C1 plus 2 C2 plus C3. So, we have taken a linear combination to be 0. Now, if this is possible, if all the CI's are 0, then this is linearly independent, but if we can get some non-zero CI's, then this set is linearly dependent. So, we have to say whether we have to check whether we are getting some non-zero CI's or not. So, this is equal to 0, again we have same equation, this is equal to 0. So, we can ignore one of this. So, we take these 2 equations and we can easily check that if we put A is equal to minus k, then B will be equal to minus k. This is a solution, general solution. General means we can vary this k for any real number. So, that means we can choose A to be 1, B to be 1 and C to be minus 3. So, if you take this C1, C2, C3. So, these are C1, C2, C3, C1, C2, C3. So, if we took C1 to be 1, C2 to be 1, C3 to be minus 3, then this linear combination is 0. So, we are getting a non-zero scalar for which the linear combination we are getting 0. So, that means this is a linearly dependent set, dependent set of vectors. Okay. This is one example where we have this linearly dependent set of vectors. Now, if we have a linearly dependent set of vector, we can easily verify that one vector can be written as the linear combination of the others. We will come to that proof. Now, we take another example where we will see whether we can get a linearly independent vector over R3 or not. So, we take another quick example. Suppose we choose S to be, this is again on R3, 1 2 2, then 2 1 2 and 2 2 1. So, this is the 3 set of vector and we want to check whether 1 2 2, 2 1 2, 2 2 1. We want to see whether they are linearly dependent or independent. So, to check that we check this is alpha 1, alpha 2, alpha 3. So, to check that we take C1, C2, C3. So, we take C alpha 1 plus C1 alpha 1, C3 alpha 3. This is a 0 vector. Now, if we this is basically give us C1 plus 2 C2 plus 2 C3 and then 2 C1 plus C2 plus 2 C3 and then the third component is 2 C1 plus this is 2 C2 plus C3. So, these are basically 0 0 0. So, this will give us 3 equations, then 2 C1 plus C2 plus 2 C3 equal to 0, then 2 C1 plus 2 C2 plus C3 equal to 0. Now, this if we write in matrix form, this is a linear equation. So, if you write in matrix form, then the corresponding we can use the Cramer's law also, because this is a homogeneous equation. Then the determinant is basically here 1 2 2, then 2 1 2, 2 2 1. So, this determinant is basically 5, which is non-zero. So, that means we have all the solution C 1 equal to 0, C 2 equal to 0, C 3 equal to 0. So, this implies this is linearly independent. This is the linearly independent set of vectors. Okay. So, now we will quickly see if we have a linearly dependent set of vector, then we can write one vector as a linear combination of other vectors. So, that is a theorem we can say, let alpha 1, alpha 2, alpha n be a set of linearly dependent dependent vectors, then one vector can be written as the linear combination of other. Then one of alpha j can be expressed as a linear combination of other vector from this set others. Okay. So, how to prove that? To prove that, we just take. So, this is a set of linearly dependent vector. Okay. So, that means we must have some CIs, non-zero CIs, not all CIs are 0. We must have some non-zero CIs such that C 1 alpha 1 plus C 2 alpha 2 dot 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 C j alpha j dot 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 plus C n alpha n. This is a 0 vector, where not all CIs are 0. If all CIs are 0, then this will give us a linearly independent set of vector, but we are taking this to be a linearly dependent set. So, now here at least one of CI is not 0. Suppose this C j is not equal to 0, this scalar. If C j is not equal to 0, then C j we know belong coming from the field, it is a scalar. Then if it is not 0, then it has a inverse, then C j inverse, multiplicative inverse will exist. Then what we do? We can write this as C j alpha j is equal to, we can take everything that side, minus of C 1 alpha 1 minus of C 2 alpha 2 like this. C j is missing here, minus of C n alpha n. Now, inverse exists. So, we multiply this both side by C j inverse. So, this will give us, this will cancel out, this will give us alpha j is minus C 1 or minus of C j inverse C 1 alpha 1 dot dot dot. So, this is basically minus of C j inverse C n alpha n. So, these are all basically scalar quantity. So, basically alpha j can be written as a linear combination. This is d 1, d 2, d n. So, alpha j can be written as a linear combination of the others. Thank you.